together do this decision tree and random forest. Okay, I would like to give a introduction to Ensemble technique, and then once we complete it for 10 minutes, then we'll proceed with the practical aspects of decision tree and random forest. Now in decision tree, guys, what we observe is that we have got only one tree. We have got only one tree. It means that that tree was helping us to classify the things into yes or no, right? Now here comes another technique called ensemble or ensemble. So people often call it in different way, ensemble, right? So if you just observe this particular picture, okay, you'll definitely have a good idea about this ensemble technique. All these ensemble techniques are based on the decision trees. Ensemble methods is a machine learning technique that combines several base models in order to produce an optimal predictive model. What is all about the several base models in order to produce one optimal predictive model? So just keep this in mind. You'll have to remember this picture, okay, when you start using these kind of algorithms. This will summarize everything. Most widely used non-deep learning algorithm. When I say DL algorithm, it is the most widely used non-DL algorithm. If you are like exploring the Kaggle kernels, I don't know how many are exploring the Kaggle kernels, make a practice of exploring the Kaggle kernels. That is how you try. You start practicing the data science projects. If I say non-DL algorithm, non-DL means what? After machine learning, we try to jump ourselves to the deep learning techniques. We also say that the advanced part of this machine learning is all about the deep learning, right? And one should have a basis in basics of machine learning, and then we go with the deep learning part. Okay, trying to build some AI-based applications, okay, which are powered with this like ML and the DL over here. When I say ML, guys, okay, so it is the conventional ML I'm speaking about, the conventional or traditional ML I'm speaking about. When I say that, so there are a couple of algorithms which are widely used nowadays. They are called as a non-deep learning algorithm, widely used. It means that before you try to use this deep learning algorithm, before you try to take a chance of using this deep learning, we first start exploring this ensemble technique. If we do not really get a result in ensemble technique, then we start moving towards the deep learning. There are so many ensemble techniques, guys. Ensemble is all about the groups. Okay, generally speaking, they're all about the groups. When I say ensemble, it's all about the groups. It says that it combines several base models in order to produce one optimal predictive model. What does it mean? These ensemble models, they're basically built on top of these decision trees. If you just observe over here, okay, just pass, just go with this flow here. We started with the decision tree now, we just discussed. And then we have something called as a bagging. And then we move ourselves to the random forest, and then something called as a boosting and gradient boosting, and then extreme gradient boosting. These ensemble techniques from year to year, they are very, very popular algorithms, okay, under conventional machine learning algorithms. Okay, so recently released XCBoost, also called as extreme gradient boosting machines. We also try to discuss as part of the syllabus, guys, we try to discuss this random forest, and then I'll tell you what is this gradient boosting and extreme gradient boosting. Okay. Very famous non-deep learning algorithms, and many of the Kaggle competition, okay, many of the Kaggle competition, as well as any projects that you wish to carry out, okay, could be the continuous target output, or it could be the categorical target output. We always try to make use of this ensemble technique. First, if it does not give us a desired result, then we move ourselves to the deep learning part. Okay, so that is the only reason we should really focus on this ensemble technique, and we see it as a most widely used non-deep learning machine learning models. I'm saying that combine several models in order to produce an optimal predictive model. See, remember, we have a many problem with this decision trees. So decision trees always tends to create a tree which has got very high depth. Okay, as I told you that as you start increasing the number of nodes, something like this, we start getting the pure partitions, trying to satisfy every sample in the data set, and finally end up with something called as overfitting. Perhaps you can actually tune this, but still we wanted to get a optimal model. If you want to get the optimal model, the other way is to create group of trees. When I say other way to create a group of trees, all about the ensemble technique. Ensemble, we always create a group of models. Okay, try to obtain the optimal predictive model. Now, in this case, what I try to do, I always start with the decision trees, a graphical representation of possible solutions to a decision based on certain condition, what we discussed earlier. And then we slowly move towards the bagging concept. Once we understand the bagging stands for bootstrap aggregating. That's basically one of the statistical techniques we normally use to create some samples in a data set. Okay. And then we move ourselves to the random forest. And I'll tell you what is the difference between the bagging and the random forest. And then subsequently, we move ourselves to the boosting, gradient boosting, and XGBoost over here. Okay, so these are the simple definitions that you should always remember, but we'll try to explore it in depth. Bootstrap aggregating. So in short, it is called as a bagging. Is an ensemble meta-learning algorithm, one of the finest algorithms combining predictions from multiple decision tree through a majority voting mechanism. What is all about this combining multiple algorithms? When I say combining multiple algorithms, we try to create multiple trees. We try to combine results from the multiple trees, trying to or ourselves expecting us to get an optimal predictive model or a better model, optimal better model. Okay, and there are different techniques for this. That's basically your bagging. Now we try to explore the bagging. Subsequently, we try to understand random forest. I'll go to the bagging here, guys. Bagging is basically called as the bootstrap aggregating over here. In short, it is called as a bootstrap aggregating. When I say bootstrap aggregating, it's something like this. Bagging, bootstrap aggregating. Okay, BAGG. Okay, bootstrap aggregating. So bootstrap aggregating or bootstrap sampling is one of the sampling techniques. Okay, sampling technique with replacement. Okay, that's the technique which is basically incorporated in this particular bagging algorithm. So even in this, okay, we try to create multiple trees, but how do we create a multiple trees? That is a point over here. We always expect to get the optimal predictive model eventually, and the trees that we try to produce should be shorter trees. Okay, because if you start increasing the depth of the tree, okay, that will basically tend to overfit. What we normally do is that we try to get the shorter trees. If we try to get a shorter trees, perhaps we assume that the problem of overfitting can be overcome. If you just observe this particular algorithm, guys, initially you may not get anything here. The algorithm works like this. This is a algorithm which is basically taken from statistical techniques for data science. Okay, so there is a textbook by I forgot the name of the author, Statistics for Data Science textbook. I can try to, I think I've already shared it. So that is a textbook. From that textbook only we have taken this particular algorithm over here. If you just observe this algorithm, guys, so let n be the number of bootstrap samples. There is a technique called bootstrap samples where we start creating some samples with some replacement. N be the number of bootstrap samples. For I is equal to 1 to n, do nothing but the for loop what we try to consider here. Draw bootstrap samples of size m, comma di. The size m will always be equal to the actual original dataset di over here. So just remember that the d here is basically the original dataset whatever we have taken, and m is always equal to the size of m will always be equal to d over here. Train base classifier hi on di. So we say that the classifier, we have taken the classifier over here. The classifier that we're trying to denote is hi. We need to train this classifier on di. So di or m is, they both are same, but remember this is going to be the original set. This is going to be the bootstrap samples. Remember, you'll have to always train. We are simply saying that train base classifier hi on di. It means that you'll have to train the classifier on the different bootstrap sample what to create. Draw bootstrap sample of size m, which is equal to di over here. And what we normally do is that coming out of the for loop over here, y hat is basically what you try to predict from each base classifier. Okay, because this is an ensemble technique, you see multiple base models trained on different bootstrap samples. We say that y hat is equal to mode of h1 of x dot 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 h1 of x over here. So we try to simply take the mode. If you could remember the mode, the frequency of occurrence of the result, right? So the more frequently occurred result will be taken as a final result from this different trees. What does it mean, guys? It means that in the ensemble technique, we try to create multiple decision trees, something like this. Okay. And these trees, remember, we try to also use a terminology called estimator. Okay, there is a terminology called estimator. Estimator is basically called as trees or models. Okay, so we try to use these trees. Okay, and then we try to find let's say that this will produce yes, this will produce no, the eventual result. Okay, this will produce yes over here. We try to consider the majority voting over here, nothing but it's going to be the mode over here. The final result from this ensemble algorithm is going to be S over here. We try to create these trees in such a way that they are actually created using the different attributes. Since we use the different attributes to create or different subset of attributes to create these trees, we expect to get a different result always. Okay, and also we try to incorporate something called as a bootstrap sampling over here. I'll try to revisit this algorithm once again, but if you just observe this algorithm, let n be the number of bootstrap sample. We try to decide the number of bootstrap samples. We try to iterate over this one. For I is equal to 1 to n, we start drawing the bootstrap sample of size m, which is equal to di, and you'll have to train the base classifier, take an algorithm and try to train that base classifier hi. Okay, nothing but an algorithm, nothing but a model on di over here, which is perhaps you'll have to train it on the m, and then finally you'll have to say something like y hat is equal to mode h1 of x dot 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 hn of x. Why I'm saying this h1 of x dot 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 hn of x, because we have multiple models in Ensemble Technique over here. How does this bootstrap sample works basically, guys? If you just try to visit this, let's say that I'll go with this bootstrap sample. Okay, so if you just observe this one, this is going to be the original data set over here. Let's call this as D over here, what we discussed earlier. It's going to be called as D, and you try to decide the number of bootstrap samples that you want to create. Okay, and what you see over here, it's like the bootstrap sample 1, bootstrap sample 2, bootstrap sample 2, 3 over here. And using this one, guys, this is the original set of what we have, like from x1 to x10 we have x1, x2, x3, x4, x5, x6 till x10 over here, and we try to make use of the bootstrap 1, bootstrap 2, bootstrap 3 over here. Bootstrap with resample, try to draw the sample, okay, with some replacement. You can see that the size of this particular data set, what we have created is basically m over here, which is equal to d in this case. Okay, we'll have to consider this m in this case and then try to train the different classifier hi. Okay, hi will take the different value like 1, 2, 3, dot, 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 n in this case. Okay, so what we can see over here, some samples are getting repeated, x8, x6, x2, x9, x5, x8, because it is trying to replace one of the sample over here, okay, and trying to generate this particular x8 again, x1, x4, x8, x2 again over here. And finally, guys, this is going to be the bootstrap samples, but remember, we are leaving some of the samples here. Those samples which are not there in this particular bootstrap set is x3, x7, x10, and then subsequently even for this we are leaving some of the samples over here because you're trying to go with a random bootstrap sampling with replacement. What you see is like x6 and x9, and then x3, x7, x8, and x10. So these are the samples which are left when you start creating the bootstraps, and what you have is like m1, m2, m3, dot, 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 emn over here. Okay, that's basically the number of bootstrap samples you have to create. These samples were left out. This is perhaps like the result what you get from this bootstrap sampling approach in statistics. And what we normally say that these samples are called as OOB samples. Okay, remember this is called as the OOB. OOB stands for like out of bag samples. Okay, so there will be always some samples which are neglected when you start creating this bootstrap aggregating techniques over here, right? So we need to make use of this different bootstraps over here and try to train your base classifier. And what I do now, I try to consider these as different training sets over here. Okay, we'll have to say how to create different training sets. So that I'll be going with this bagging classifier over here. When I say bagging, it's called as a bootstrap aggregating. Bootstrap, you already created a bootstrap samples. You can observe over here, this is going to be the training set, and you've created many bootstrap samples such as T1, T2, dot, 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 till Tn over here. And then you have the classifiers such as H1, H2, dot, 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 Hn over here, nothing but the classification models. And you'll have to start training the models on this bootstrap samples T1, T2, dot, 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 Tn over here. And what I can expect from this is nothing but the predictions from this model, such as your Y1 hat, Y2 hat, dot, 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 Yn hat over here. So these are the different predictions what you can expect from the different base classifier trained on different bootstrap samples. And finally, guys, we try to adopt the majority voting over here. And finally, we say what is the final predictions, Y subscript cap or hat, which is equal to mode of h1 of x, h2 of x, hn of x, where hi of x is equal to y high at in this case. We try to always make some predictions by just passing this new data parallel over here once it is being trained. When I say bootstrap aggregating, we have created the bootstrap samples. And what is all about aggregating, guys? Finally, we get the result by just trying to consider aggregating the different base classifiers or the classification models we have created. That is the only reason we call this technique as a bootstrap aggregating. Now, the point is that why we are shifting ourselves from decision tree to the bagging. And we also said in the beginning that if we start creating the multiple trees, we end up with the optimal tree. Okay. We imagine that, or we assume ourselves that if you try to create the multiple trees, probably you can expect to get an optimal tree model, okay, over the single decision trees. We will see why we are saying that particular point. Now, this is the bagging, which is not discussed in this course, but theoretically you'll have to understand before we proceed with the random forest. I'll try to go with the random forest. Random forest is all about completely based on this bootstrap aggregating concept. They try to incorporate or try to follow the bootstrap aggregating over here. But there is always some kind of randomness in this recreations. Remember over here, guys, I've taken a definition saying that random forest with random feature is formed by selecting at random at each node a small subgroup of input variables to split on. I've taken a simple definition saying that random forest with random feature is formed by selecting at random at each node a small group of input variables to split on. What does it mean? If you just observe over here, so it is all about the bagging with respect to trees plus random feature subsets over here. So I've taken one simple example here, guys. In bagging, we do not have the option of choosing these features randomly to create or to select these nodes over here, decision tree nodes. What we normally do is that we have these features like sepal length, sepal width, petal length, and petal width. In this particular data set, out of these 4 features, we are not going to choose all the features to decide the best attribute over here. We will try to choose that randomly. Okay, we'll try to choose that randomly. And of course, the bootstrap sample is also incorporated over here because it follows the bootstrap aggregating again. But we say that it's going to be like random feature subsets. That's the only reason selecting these features randomly to decide the nodes of your tree. We call this approach as a random forest. Why do we call it a random forest? It's a fancy term, guys. Forest is all about the collection of trees, isn't it? So it's nothing but the ensemble again. So in a forest, we have multiple trees. How these multiple trees are created? These trees are created by choosing the bootstrap sample or following the bootstrap aggregating technique. At the same time, we also try to make use of random feature selection, okay, to decide the nodes of your tree. Decide the nodes of your tree intrinsically. That's basically done intrinsically by your decision tree algorithms, okay, which is perhaps your random forest in this case. We start building these trees, and then this is what we call as a random forest. Okay, so if you start creating this, features randomly, then perhaps like you'll always have an advantage when you have a randomness in your tree. Then you can always expect a good predictions from the different models over this bagging. So that is the only reason we try to go with the different random features formed by selecting a different features randomly over here. So guys, this is like the ensemble technique, the bagging and the random forest. But what is the advantage of using these techniques? As part of a syllabus, we try to explore this random forest. What is the advantage of this one? Here comes the concept of bias and variance example. Let us try to complete this because, as I told you earlier, your decision tree always tends to overfit. We want to understand this bias and variance example, and then subsequently we try to map what is the overfitting and underfitting. Once we understand those concepts, we can subsequently move ourselves and try to say how this ensemble technique are helping us to get an optimal predictive model over here. In this case, guys, if you just observe here, I've taken a couple of examples. One is the bias and the variance over here. Okay, the bias and variance are all about the 2 errors you normally see in any machine learning models. They are the errors. These 2 are the errors you always see, and we typically call as a trade-off. Okay, remember the bias and the variance, they are always the trade-off graph. Okay, when bias increases, the variance decreases. When variance increases, the bias decreases. What is all about this bias and the variance, guys? Now we just observe here. I've taken some couple of examples in this slide over here. So where what you can see on the left hand side is some points, okay, and there is a curve over here which is trying to show us the true relationship between your x and y. It means that there is a true relationship approximately saying that this is going to be like x and corresponding y over here. This is going to be your x and corresponding y over here. Now, what we do is that to understand this bias and variance, we try to consider this x on the x-axis and then f of x, nothing but the function of x. That could be any functions. You can also consider any mathematical functions over here. That could be like f of x, which is working on this x. So let's call that as the true or target functions, where f of x, nothing but your y, okay, is some true or target functions. Remember over here, we always want to show this true relationship between your x and y. Will it be possible to show the true relationship between your x and y? That's always our concern, trying to show the true relationship between your x and f of x or y. Now we have a true function over here, guys. We have a true function. Imagine that there is a true functions. This orange line, we call it as a true functions, okay, which shows the true relationship between your x and y. And we do not really have access to this particular true functions. Remember, we do not really have access to these true functions. Okay. When we do not have access to these true functions, what we normally do is that we try to model an algorithm and try to find the true relationship just like this. I'm actually taking the gray line over here. It means that we do not have a true access to this true functions. If you just observe here, let me try to plot a regression line. When I say a regression line, you can see over here in the legends have taken, this is the gray curve is basically the true functions, and then your blue points are nothing but the train set over here. So trying to plot a regression line like this, the regression line always, or regression algorithm always suffers with this high bias. High bias, nothing but it is not able to explain the true relationship between your x and y. Okay, so you have drawn this line, and then there are a couple of points over here. We just compare this curved line with that of the regression line. So the point is somewhere else, so the point is somewhere else over here. The point is on this, couple of points are represented more properly, but there is always a kind of differences between this. Okay, the true points and the points which are predicted over here. When you're not able to explain the true relationship between your x and y, then we say that there is always some kind of bias in your model. And remember the point over here, guys. Your linear models will have this high bias in it. Okay, high bias in it. Imagine that this is going to be during the training phase. Okay, imagine that this is happening during the training phase of your model. Okay, this is happening during the training phase of your model. So when you try to draw a simple line over here, what I've written is that where f of x is some true or target functions, the blue dots are training data set. Okay, here suppose if you fit a simple linear model, okay, in terms of linear regression or a decision tree stump. But when I say decision tree stump, it is all about a node with only one split over here. Okay, remember over here, guys, if you see a simple stump like this, okay, this will also not be able to explain the relationship between your x and y. So in the context of linear regression, I'm calling it as a linear model or a straight line, whereas in the context of your decision tree, I'm calling it as a stump or decision tree stump over here. But anything is okay for us, but what I've taken is a linear model, and that is going to be during the training phase, which is giving us a high bias model. Whereas we are not able to show this kind of true relationship using this high bias model. Let us try to consider a decision tree, and I call that as the unpruned decision tree over here. If you just observe over here, guys, this is also happening during the training phase. Okay, this is also happening during the training phase. What you can see over here, it's a bias and variance example, and then we have a true function. We already have a true functions over here, and we have a training data set, something like this. And you can observe here the high variance model. It's a high variance model. It is trying to explain every distributions of your data points. That's basically called as a high variance model. If you can see over here, I'm trying to say that it's going to be the unpruned trees. It means that you have a tree, okay, which has got very high depth over here. These trees is called as unpruned trees because you're not eliminating a couple of branches from this trees over here. When you try to consider this kind of unpruned trees, what you see is like the points are actually, or the relationship between the x and y are shown something like this. It's a kind of squiggly line, what you see over here, okay, where you can see that perfectly shown with the representation, the relationship between your x and y. Okay, you can see that this is the true function. Okay, whereas the tree, the unpruned tree, what you can see over here. Okay, so it's showing us all the relationship between your x and y, and typically we call it as a high variance model. Remember over here, your decision trees are always, it could be the simple decision trees, it could be any ensemble technique you're trying to make use of. They are all like the high variance model. Keeping this high variance model is always a problem. It means that during the training phase, they are really working well. We are really happy with that. If you see, observe over here, there are a couple of points in this training data set. Trying to explain every point like this will definitely give us 100% accuracy when I try to check for on the training data set. What if we want to check the model's accuracy during the test phase? These kind of high variance model will literally fail during the test phase because it will not be able to explain the true relationship between your x and y during the testing phase. We always see this kind of problems in your decision trees. Okay, we need to actually fix this problem. It means that either we'll have to go and then try to prune your model. Okay, and probably pruning your model, you can expect to get a good performance from your model during the test phase also. Let's say that, guys, you have a significant difference between your training accuracy and training test accuracy. You have this 100% accuracy during the training phase, and then your accuracy literally drops to 60%, 50% during the test phase. This is not entertained. Okay, it means that maybe your model is overfitting over here. The different cases, okay, to consider that your model is basically overfitting, nothing but high variance model, okay, performs really well during the training phase but fails during the test phase. And underfitting is completely opposite of this. Completely opposite means what? It will not perform even during the training phase. It will not perform even well during the training phase and also during the test phase. What we want is an optimal model. Wherein it performs well during the training phase and also well during the test phase. We always expect to get this model, and that is a tedious job again. To control or to get this optimal model, you have to always control your bias and variance. As I told you earlier, bias and variance are always the trade-off. Anyhow, guys, this is what we see as a high variance model. But let's try to consider what usually happens when you go with this bagging, okay? Bagging concept when you have this high variance models. But before that, let's say that this is happening during the training phase. I'll try to consider a couple of test data points in a different color over here. Let's say that this is what you see during the training phase, and what you get is a high variance model, which is decision trees. Let's try to consider a couple of test data points, okay? So somewhere in this region over here, okay, when you consider a couple of test data points in this region, what you can see is these are the test data points. We want to make some predictions on this, and what you can see over here, it's going to be like a very large error. Okay, so whatever you have predicted and whatever you have as the actual values over here. Okay, you can see the differences over here, the distance between the actual line, actual point, and the point, whatever you have taken over here. This is happening during the test phase, and your model is not performing well during the test phase. This usually happens when you start using the decision trees. I'll go back and I'll try to explore your regression models. Usually we say that regression models are low variance model, remember? So high bias during the training phase, but low variance during the test phase. Let's say that I am going to consider this examples over here. Okay, so we are not trying to draw a squiggly line, but it's nothing but a straight line. When I try to find the distances between this point on the line and the point, actual point, so this seems to be very less when you just compare with the previous model, whatever we discussed. It's going to be like a very low variance. Okay, so during the test phase. So that is why your linear models, okay, linear models are high bias and low variance model, and we try to use this linear models initially for any continuous data predictions, but as alternatives, we always have the decision trees. Keeping this in mind, the variance and bias, the high variance models are also called as the tends to give us the overfitted model or over specialized model, trying to satisfy every records. Okay. And combining this or keeping this in mind, we try to go with, so why does bagging generally or random forest works well for us? Even though we are saying that these techniques are giving us a high variance model, we'll have to say something like this. We'll have to understand this concept, something like this. If you just observe over here, guys, I've taken a graph on the right and left hand side and the right hand side. We know that in the bagging or random forest, what we do, we try to create some bootstrap samples. We try to consider this true functions over here. We wanted to always try to get a true function. That is our intention. And then what you can see over here is like the different training sets. So what we do in bagging is that we try to create a different bootstrap samples. We have this train set 1, train set 2, train set 3 represented in different colors over here. We have these points plotted something like this. Okay, let's imagine that we try to go with this bagging or random forest. We know that we try to train the different classifiers like H1, H2, H3 on different bootstrap samples on, let's say that could be the training set 2, training set 3 over here. When you just start training over here, what you can see is again the high variance models only, because you try to see that the models are satisfying all the points over here. The first model, let's call this as H1, H2, and H3 over here. And all these models are trying to satisfy all the points in this case. But this will definitely produce the high variance model. But eventually, when you have the high variance model, this high variance model will definitely help us to get the optimal model. It means that keeping the high variance models in our mind, you can always get the optimal model. Let's say that if you just try to take the average of these models, okay, average of these models, the different H1, H2, H3, the result of average of these models, then you can always expect to see that you are touching this true function. Okay. So you can always expect to get a optimal model by taking an average of this high variance model. Okay, the intention is something like this. Going with a bagging or random forest, what we normally do is that we always try to take an average of these different models. And what we can see is that when we take the average of these models, we can always expect to get an optimal model. That is the only reason for going with this, bagging or random forest. Okay, so trying on different sets and trying to get a high variance model, trying to take an average of it, you can expect to get a optimal model, which is very close to the true functions, what we can see over here. That's basically why we use this bagging. And this is also one of the interview questions, what we normally see when you say that, bagging or boosting or random forest. Here comes the final one, which is basically the pros and cons. It reduces overfitting in decision trees and helps to improve the accuracy. It is flexible to both classification and regression problems. It works well with categorical and continuous values. Okay. Reduces overfitting because we have this high variance model, try to get the average of this, and we can see the optimal model, which is close to the true functions. Normalizing of data is not really required. Remember the point. This is a rule-based algorithm, guys. Whenever we consider data set, and data set features have different range of values, you need not to consider standardizing or scaling this data set, because it is all about the frequency of occurrence of the classes and thereby calculating the Gini or purity of partitions. The cons is always like high computational power, as well as resources as it builds numerous trees to combine their outputs. So you are going with the multiple trees because this is an ensemble technique. When I say ensemble technique, it is all about like building many trees, not only 2 or 3 trees, but hundreds and thousands of trees will be able to create. And if you're trying to create many trees like this, perhaps it will definitely require very high computational power. This will definitely take high computational power because you are going with multiple estimators. I'm also using the term here called as estimators or models. It also requires much time for training, as it combines a lot of decision tree to determine the class. So training time is always high, even for this particular ensemble techniques. Due to ensemble of decision trees, it also suffers interpretability and fails to determine the significance of each variable. Remember, this is like a black box. We are not able to identify what's going inside your decision trees. If I say 100 trees or 1,000 trees you're going to create in ensemble, will it be possible to interpret the decision trees using this in this bagging or like the random forest. It's highly difficult or highly impossible to say what's basically happening within each tree and how or what is that variable which is really important for our constructions of the tree, right? So it suffers from interpretability, whereas in the decision tree we said that building one tree can be visualized and we can always try to say that it's very easy for us to interpret. But whereas when you go with this kind of ensemble technique, it's again a very complicated kind of calculations, and this will definitely suffers with the interpretability. That's what you have to always remember, guys. So that's basically the pros and cons of decision trees. And next is the boosting. Okay, before we go to the boosting, okay, I definitely want to take the practical aspects of this. And then we proceed, once we complete that, we proceed with the